Hello and welcome everyone to today's webcast on Spark-Centric data processing in the Google Cloud Platform. Thanks for taking a few minutes to spend with us today. We have some really interesting topics on Spark lined up for you, so let's get started. Maybe a short introduction to ourselves. So my name is Scott Stieritz. I'm joined today by my colleague John Miller. John and I are both data and analytics consultants at Thoroughgood, based out of our US offices, and we'll speak a bit about our office locations and Thoroughgood as a whole in just a minute. John and I both have a lot of experience and interest in data and analytics projects, especially those using Spark for both data engineering and data science, and doing so across cloud platforms. So we both find the topic of Spark as a whole very interesting. We're excited to talk to you today about Spark and more specifically how we can best make use of Spark within the Google Cloud Platform. I've added our contact information up on the screen here, so feel free to drop us an email, reach out via LinkedIn, anything like that. We'd be happy to answer any questions you might have or generally set up some time to chat. So let's take a quick look at our agenda for today. I mentioned we'll give a brief introduction to Thoroughgood, so we'll begin there for just a minute or two. Then we'll get to the main topic we're focusing on today, which is Spark. We'll look at Spark as a whole, then how Spark can fit into a modern data architecture, and look at some specific tooling for using Spark within the Google Cloud Platform or GCP. There have been some recent advancements in terms of serverless Sparks. We'll also look at what that is and how we can benefit from it, and then we'll have a bit of a wrap up at the end. Like I said, we'll start with a brief introduction to Thoroughgood. So for those of you not familiar with the firm, we're an independent specialist data and analytics consultancy. Within data and analytics, our consultants are experienced across the areas of data engineering, data science, and data visualization, and our services similarly span that breadth of the data and analytics landscape. So everything from architecture design and implementation to specific solution design and development to hands-on advanced analytics and data science services, all the way through to things like defining data strategies, user empowerment, and training in key data and analytics topics for the people in our customers' organizations. We're a global organization, so the company's based out of London. We have offices in Philadelphia and Boston in the US, where John and I are located, as well as offices globally in Singapore, Sao Paulo, Brazil, and Bangalore, India. At Thoroughgood, our approach is in combining business focus and business understanding with our understanding of and deep experience in the range of technical possibilities to drive business value with our customers. I mentioned that we're an independent consultancy, which means while we partner with many of the leading companies in the data and analytics space, we're not tied to one technology or one platform in particular. Rather, we have experience across a wide range of technologies, which allows us to understand the business goals and the data landscapes or even the future data strategies of our customers in combination with experience in the technical possibilities to identify and design the optimal business solutions. And I've just put a sampling of technologies that we commonly work with up on the screen here, which is of course a non-exhaustive list. And while we are Google Cloud partners, we also work with many of the others that you commonly see in these types of data use cases. Before we talk about Spark data processing on GCP or the Google Cloud Platform, I think it's important to provide a little bit of background on Spark. So what is Spark? It's an open source big data processing framework. It came out of UC Berkeley's AMP Lab. It was then open sourced, and now it's managed by the Apache Software Foundation. In general, Spark kind of continues to evolve those distributed compute concepts, which some might be familiar with from things like Hadoop, but Spark adds some additional performance improvements in a number of instances due to its focus on processing data in memory. Spark was written in Scala, and it uses JVM, or the Java Virtual Machine architecture, so it comes with integration with languages like Java, of course Scala, but it's also been integrated via Spark APIs into languages that many of us are probably familiar with when it comes to data manipulation and data analysis, such as Python, R, and SQL. Because of its processing power, we've seen Spark's usage growing massively in the data and analytics space across both data engineering and data science use cases. And I'd say that many, if not almost all of our customers are either using Spark actively in one way or another today, or in the process of building towards Spark-centric cloud data architectures to harness this power for their business processes. So we talk about Spark and its value as a distributed compute framework, but what does this really mean and how does it work? Well, to help me explain, I've just grabbed a diagram from the Apache Spark documentation, which gives a simplified view of the underlying structure, which I've put up on the screen here. At the most basic level, we can think about writing some data transformations and maybe even executing those transformations locally, for example, on my laptop. And maybe this works fine for smaller data sets. Maybe I have an Excel file with a few thousand rows and I write a Python script that connects to that file and does some transformations. But as my data set sizes start really increasing, this takes longer and longer and longer to run on my laptop. Now, wouldn't it be great if rather than waiting for my own laptop, which is just one computer, to execute the transformations, I could get 2 computers to do it more quickly, or 3. And that's the idea that Spark and really any distributed computing is built upon. Rather than executing some process on one computer, let's think about executing the process on a cluster of computers, which can each pitch in and complete the process much more quickly than I otherwise could. And I mentioned this diagram, and that's what this diagram is representing, a cluster of computers that are working together to execute some process. Now, again, for comparison, if I go back to those transformations I'm executing on my laptop, and I open up another laptop just right next to mine, I put the same set of data on it, and independently, I just click run on both laptops at once. Am I going to finish my computations any faster? Well, of course not. They're not talking to each other. They're not working together. They're just running the same thing twice. So what I really need is some framework that can manage all of the different machines in my cluster, orchestrate them such that they're executing different parts of that overall process in parallel, and therefore finishing the overall process in a fraction of the time. And that is what Spark is. It's that framework that divides up the steps of my process, distributes subsets of the data as needed by each of those machines or nodes, as we can see on the screen in my cluster, and it directs each of those nodes to execute those tasks in parallel. So within my Spark cluster, I have my driver node, which is giving me my single interface into the Spark environment, where I can write all of those data transformations or maybe machine learning scripts in any of those languages that we talked about a few minutes ago. It creates an execution plan, and it uses that plan to distribute all of that work or the data and the processing across all of the available worker nodes in my cluster. Once those worker nodes finish those tasks, they'll also be reporting their own individual results back to that driver node, which can then aggregate up the results depending on the logic of the transformation applied and return it back to me, again, through my single interface. And in the middle of all of this, we have a cluster manager as a part of the Spark framework, which works alongside that driver node to allocate the resources from the worker nodes to the individual tasks that make up my overall process. So I gave that basic example throughout of my laptop or a set of 2 or 3 laptops. In reality, in the modern world of cloud computing, the machines in that Spark cluster are much more likely virtual machines in the cloud. And I can have 10 or 20 or any number of machines in that cluster, which each could be 10 times as powerful as my laptop. And I can scale that up or down or optimize the characteristics of those machines based on what I'm actually trying to do within my process. So I hope this is what really starts to indicate the power and the value that Spark processing can really unlock and why we care about designing with Spark centricity in our modern data architectures. So speaking of modern data architectures, now that we have a clear understanding of what Spark is, let's see how it's applied within the Google Cloud Platform. We felt like it would be good to start with a generic modern data architecture, and then we'll dive into different parts of the architecture where Spark can be leveraged, especially in GCP. And we see on the screen here what you might imagine as kind of a generic, high-level, end-to-end architecture, and in this case, a data lake-centric architecture. And we start with our source data over on the left-hand side, we kind of move that data through the layers of our data lake, typically with some automated orchestration, and eventually ending up in reporting and being exposed to end users. In addition to that pathway, there's also tools for data scientists and business analysts to access data at varying points in the architecture to conduct analyses or build machine learning models. And now I've added in a couple of components to help illustrate how this architecture can be thought of in terms of Google Cloud Platform resources. Now, in just a second here, John's going to dive into these tools in a little bit more detail. But for example, we can see things like Dataproc, which can leverage Spark for data movement and transformation across the varying layers of our data lake. BigQuery, which is a data warehousing tool, which can also integrate closely with Spark for data engineering, ad hoc querying, and providing a relational layer through to the data that's living in our underlying data lake. Vertex AI, which is an end-to-end data science platform that manages the entire machine learning lifecycle and can use Spark for model training and inference through libraries like Spark ML. And Dataplex, which provides a unified data fabric across our entire data landscape and can support fully managed serverless Spark processing through the Dataplex data exploration workbench. We can also see these Databricks logos that are distributed throughout the screen. So while Databricks is a third-party tool, it's also available on and well integrated into the Google Cloud platform as well. And we see many companies using it within their GCP architectures or architectures spanning multiple cloud platforms as a premium option for nearly all of those Spark use cases across data engineering and data science. So I'll now hand it over to John, who will be diving into individual Spark components on the Google Cloud platform.
Thanks, Scott. Like you said, I'll be diving into some of the components right now. A little bit on Spark on Google Cloud and the rise of open source first. So open source adoption in data analytics is increasing rapidly. Based on a BCG study, 99% of Fortune 500 companies currently use open source software. 80% of IT departments will increase the use of open source within the next 12 months. 35% of all enterprise software is based on open source code. Hence, we see the open source adoption in data analytics is increasing rapidly. As companies migrate to the cloud, they're integrating open source analytics and processing into their core data strategy. What this means is that organizations expect the same ease of use, scalability, and security from the open source platforms as from other cloud services. So just because it's open source no longer means that it can have a lower quality of service or security. Google Cloud has been working to help users build Spark-based solutions for all workloads, so ETL, data science, and data exploration. Google Cloud has launched the industry's first auto-scaling serverless Spark, which is the core of these offerings. Serverless Spark is a cornerstone of what a modern cloud service is because users do not have to manage the clusters in the cloud. This enables them to move away from any infrastructure management to focus solely on code development. Understanding that users prefer different interfaces, Google Cloud has made Spark pervasive by integrating Spark with BigQuery, which is our cloud data warehouse, Vertex AI, which is our data science platform, Dataplex, which is used to build data fabrics, and Dataproc, which is used to run Spark workloads. With this integration, users can seamlessly use Spark from their interface of choice. In addition, based on the organization's data deployment strategy, users can use serverless, Google Kubernetes engine, or compute clusters for any Spark applications. So we'll start going through some of these different GCP resources to learn a bit more about how Spark is involved. So the first resource to call out is Dataproc. Dataproc combines the best of open source and cloud because it's a fully managed and highly scalable service for running over 30 open source tools like Apache Spark. So Dataproc enables you to take advantage of open source data tools for batch ingesting, processing, loading, and querying big data. It is also a managed framework used to coordinate cluster creation, management, and monitoring in a fast and easy way, all in one place. It is integrated with the other Google Cloud tools, facilitating the usage of open source solutions alongside native GCP services. Additionally, Dataproc is a pay-as-you-go service, so you can optimize costs, eliminating charges for capacities that are not being actively used by turning them off. It also does offer the flexibility of choosing to create and manage your own clusters whenever infrastructure control is required, or if it's not necessary, you can choose to spend time focusing only on your data by simply specifying workload parameters while Dataproc provisions and auto-scales the resources that you need. If you were to compare an on-prem instance of Spark and Hadoop against an instance of Dataproc, you would see the benefits of using a platform as a service offering. It offers you speed and the potential cost savings compared to manually configuring the on-prem version. Now I'm going to hand it back to Scott for a short demo about Dataproc.
All right. So as far as the demo of Dataproc, I figured we'd follow a similar architecture to what we had seen, kind of in that high-level architecture view from a couple of minutes ago. So I have my central data lake, we could say, which is in Google Cloud Storage. I have a couple different folders within that data lake, which are just meant to be representative of the different layers within that lake. So I have a raw layer where I've brought in, just some sample data that I've used as a sample for these types of tools before. Maybe we're a consumer packaged goods company where we're tracking our sales. We have some files that come in annually that capture those sales. We have information about the overall orders and sales. It captures individual line items, which makes up those orders. And then we also just have some dimensional information about our customers. So things like the customer name, maybe any addresses about those customers, anything like that. So I've loaded that all into the raw layer of that lake. And again, we have some other layers like processed for just kind of bringing in and transforming that data, maybe getting it into some interoperable open source file formats to work well with Spark and work well with other components of a data architecture. And then finally, an enriched layer where we're more bringing together the data for use in some downstream reporting or data applications. Now, I want to use Spark processing within Google Cloud Platform to process and transform this data. And I'm going to use Dataproc for doing that. So within Dataproc, I've already created a cluster and I have this up and running just for use within the demo today. But I could create another cluster where I'm selecting what infrastructure service I'm going to use. In this case, I'll use Compute Engine. I can give a name to my cluster, maybe select the region that I want to put that cluster in. If you recall from that Spark kind of architecture diagram where there's the driver node and then a number of worker nodes, I want that type of setup. So I'm going to use the standard cluster type where I have one driver and any number of workers that I would want. I've already defined an auto-scaling policy. So I talked about the scalability of Spark and especially the scalability of Spark within Dataproc and other GCP services where I can get more worker nodes added to my cluster if I want, or I can scale that back in and have fewer nodes in there if the processing that I'm doing is a little bit smaller, doesn't require the spend as I'm spending on that, consumption of the underlying resources. So I could scale it back down or scale it out to match the amount of processing power that I need. I can choose the version type for any of my nodes. In this case, or the image that I want to use. In this case, I'm just going to select any of these images that have the latest version of Spark available on Dataproc, which would be 3.3. So I'll just pick that version type. I also want to be able to interactively interact with my cluster. So for that reason, I'm going to enable Jupyter notebooks within my cluster so that I can use those notebooks to query the data, explore it a little bit, and build out my transformations that I'm going to use. And I can set some additional configurations here, like I could set the different node types. I talked about how much you can scale out the individual machines as well as number of machines. So scaling out the individual machines, I could take some massively powerful ones or some much smaller machines, again, kind of depending on what's been optimized for my specific process. So I can set all that. There's a few additional cluster configuration options, but I'll go back to the cluster that I have created, which is this one that's already up and running. And we can see some of the configuration settings within that cluster of just type of nodes that I've selected or types of machines to use as those nodes, number of nodes, the scaling policy that I've assigned. And I can go to this web interfaces tab here. I mentioned that I've enabled Jupyter notebooks on this cluster. So I can then just click on the Jupyter notebook link, which brings me to my interface here where I can see a PySpark notebook that I've created just within to run on this cluster here to, connect to the data, do that exploration and do some of the data transformation that I'm interested to do. So this is a look at the notebook itself. Maybe while I'm talking through this, I'm just going to click run all to get all these steps running. And in reality, when we're seeing this as a productionized business process, we would probably see these different types of activities split out into different notebooks, split out into different processes. But for the purpose of this demo, I've just combined them all into one notebook today. So maybe I want to start with a little bit of initial data exploration. And I've just written a very short Spark script here using PySpark, or Python's integration of Spark, to connect to one of those sales files, the sales file from 2019, to just read that in using Spark and show the top number of rows within a data frame that I've loaded it into. So I can see things like the product that's been ordered, the line number within the sale that's associated with that product, the quantity, the price of the product, and the overall order number to which it's associated. And maybe I'll take a look at one other sales file, and I can see that the schema of those files are pretty well matching up. I have the same columns in each, looks like similar data types in each, which is good. And then as I move from that initial data exploration toward actual data ingestion and processing, maybe one thing I want to do is load all of my raw sales data to that processed layer of my data lake. So first I'm going to connect all those files, bring them into and combine them into a single Spark data frame, which I've just called sales here. And I've just run a quick count on there to make sure that I have some visibility into how many records are being brought in. And finally, maybe I'll write that out using open source file formatting like Parquet, write that back to my data lake, but rather than writing back to the raw layer where it came from, I'll write to that process path, the process folder back in that Google Cloud Storage bucket. And I'll put it in this fact subfolder there and label it as sales. Maybe I want to do the same thing with raw orders and raw customer data. I just want to load them in, do a very, very light cleansing and kind of transform them into some open source file formats and add them into the process layer of my data lake. Maybe finally, in case I want to pick it up for any downstream reporting or data applications, I'll also calculate the last refresh date so we have some visibility into when all of this data was last loaded through the data lake. And then finally, again, in reality, maybe a separate notebook or separate process entirely, but I'll want to pick up each of those different data points and kind of cleanse and combine them for something that's actually useful to feed into an end state reporting application. So I can see the sales data that I'm reading back from that process layer. And again, that row count seems to be matching. So I'm making sure that I'm bringing in all of the data that I have, doing the same thing with orders and customers, bringing it in from those Parquet files sitting in the process layer. And then maybe I'm doing a final join into a combined data frame here, where I'm just taking my sales data, joining it with my order data. We can see that there's that shared order number field between the two. So I'm just using that to join in the order information, such as order date and the order status, into each of those line items. And doing the same with customer data, using that customer ID field that's shared between orders and customers to join all my customer information into the underlying sales data. I've just converted it to a pandas data frame just to make it a little bit easier to print out onto the screen here and to scroll across. So I can see all of this combined data where I have things like customer ID, order number, which were some of my join fields, the sales total, quantity, price, which I remember came from my sales data, but also things like order and customer information coming from those other sources. And now that I have this final Spark data frame, I'm just going to write that out to the enrich layer, knowing that I want to maybe build a reporting solution on top of that, which will pull from that enriched layer into whatever visualization tool I've used. So that's what I wanted to show on the demo. And I think back to John to talk about a few other tools that leverage Spark within the Google Cloud Platform.
So moving on from there, we will go into BigQuery as the next resource that we wanted to highlight. So BigQuery is a completely serverless and cost-effective enterprise data warehouse that works across clouds and scales with your data. BigQuery ML, BigQuery Omni, and BigQuery BI Engine are all built-in capabilities that allow you to build ML models, analyze and share data across clouds, and conduct real-time analytics with streaming data pipelines. BigQuery's Spark features currently are in preview, and those are BigQuery's stored procedures for Apache Spark, integration of a PySpark editor within the BigQuery console, and the ability to surface the data stored in BigLake to Apache Spark compatible data processing systems via Spark BigQuery connector. So going into each of those three features a bit further, what previously required Scala or PySpark capabilities is no longer the case moving forward because users will be able to call Spark stored procedures directly from BigQuery. This is a move beyond using only SQL in BigQuery as a way to make Google's tool more dynamic and powerful for the different analyses that users are doing. You can see in the image that the stored procedure, you can set the engine type in the stored proc to allow BigQuery to leverage the power of Spark. Google has integrated a PySpark editor into the BigQuery console, powered by Serverless Spark backend. Users can write and submit PySpark code from BigQuery, see the results in the BigQuery console, and get the same serverless auto-scaling experience that they're used to with SQL. And finally, BigLake is a storage engine that extends BigQuery's storage capabilities, such as fine-grained security, performance caching, and sharing to open formats on multi-cloud object stores, all while making it uniformly accessible across open-source engines like Spark using connectors in BigQuery. The image on the right here shows creating a BigLake table in BigQuery by connecting to a data source stored in Google Cloud Storage, which can then be surfaced to Apache Spark systems via the Spark BigQuery connector. Moving on, Vertex AI is an end-to-end machine learning platform to build, train, deploy, and scale ML and AI models. At its base, it's a Jupyter Notebook as a service, which comes with additional benefits of some MLOps tools. And Google has created some serverless components in Dataproc that can be leveraged in Vertex AI for Spark, PySpark, Spark SQL, and Spark R batch workloads. The utility of Spark in Vertex can be seen in the full life cycle of the project. You can explore and prepare your data using Dataproc Serverless, and then train, evaluate, and iterate your model using Spark Library MLlib, and then you can deploy and monitor the models after you develop them. The final resource that we'll touch on today is Dataplex. Dataplex's data fabric helps to power analytics at scale by democratizing data across the organization while maintaining a central location for monitoring and governance. In the Explore workbench within Dataplex, users have the ability to query data using Spark SQL or Jupyter Notebooks, as well as seamlessly collaborate across teams. Explore provisions, scales, and manages the serverless infrastructure required to run your Spark SQL scripts and notebooks using user credentials. You can operationalize your work with one-click serverless scheduling from the workbench. The image on the left here shows a Python notebook with pandas for data exploration, whereas on the right, you can see a Spark SQL script to explore the data. Much of what's been shared so far is referencing serverless Spark. As such, we feel it's important to understand why much of GCP's Spark offering is serverless and what that means for the user. With serverless Spark, you still get the same functionality of using Spark clusters, but without the need to manage them. After you submit the Spark job, it auto-provisions and scales clusters based on your needs. Some of the benefits here include flexibility, so auto-provisioning and scaling enables you to run jobs of varying size and complexity without having to change your managed cluster settings, or worse, pay for a large cluster even when you don't need all of that processing power. Bringing me to the next benefit of cost. With serverless, you're only charged for the periods that your workload is in execution, so depending on your use case, this could result in cost savings. Next, we have focused. Your developers are now empowered to focus on their specific function instead of needing to manage the backend architecture. And finally, speed. Since they're not worried about the backend, developers can move faster through code updates. On the other hand, there are a few drawbacks to consider when going with serverless. There's a loss of control. Since it's managed by another company, your organization will have to relinquish some of the control of the overall process. With that comes some potential privacy concerns. While separated, serverless does use a shared cloud environment, so there is a potential risk of data accidentally being accessed by someone outside of your organization. And additionally, when you don't have control over the full end-to-end architecture, it can be more difficult to identify where a problem is coming from and how to exactly fix that. So to close, I'd like to talk about some next steps in your data and analytics journey. If you're curious about how to get started with Serverless Spark, Google Cloud has created a repository of solution accelerators built around common use cases. These are easy to use open source proof of concepts. If you have any questions about these, you can feel free to reach out to myself or Scott to discuss your use case and how these could be leveraged. At Thoroughgood, we specialize in analytics, data science, machine learning, AI, and more. If you're looking for help in any of these areas you see on the screen right now, you can feel free to contact us. As I mentioned during the introduction, we come from a business-focused perspective and tailor solutions to best fit the needs of our clients. I'll share our contact info again on the final screen if you'd like to reach out to us via email or connect with us on LinkedIn. Please feel free to do so. You can also reach out to us through our website at Thorogood.com. So wanted to thank you again for tuning in today. Please feel free to reach out to us. Our contact info is on the screen there. Thank you and have a great rest of your day.